Okay, welcome back. This is the third example of solving differential equations that are separable. In this particular example, there's going to be an interesting thing that happens with the domain. So hopefully you make it all the way to this example, and of course if you're watching, you probably have. The first step is going to be to multiply everything by dx. So we will take care of that real quick. So we're in the process of separating the variables here. Notice again there's no x term over here, but that's okay. We get 1 over 3y squared. It's looking like this isn't going to be too bad. We are now going to multiply both sides by 3y squared, which will eliminate it on the right side and make it show up on the left side. Alright, so we're now at 3y squared dy is equal to x dx, or 1 x dx, I should say. So step 2, which is to separate the the variables, is done. The next step is to take the integral of both sides. So the integral of 3y squared, luckily this isn't too bad, is going to be y to the third, that's it, equal to x plus c. So we've separated variables, integrated with respect to each variable, and used initial condition to find c. Initial condition is going to be 1, 1 in this case. So if we replace 1 equal to 1 plus c, so we replace y, that's cubed technically. 1 equal to 1 plus c, of course, is going to give us that c is 0, which is awesome because that means that our answer is actually simply 3y cubed equals x, and that's it. But the second to last step is to solve for y, so we'll take the cube root of both sides so that y equals the cube root of x. And this looks like pretty, I mean, it looks pretty good if you think about it. Does it have a discontinuity? Cube root could be positive, negative, or 0. It doesn't have a discontinuity. But I want you to take a look at the original differential equation they gave us. Sometimes you have to do this. If you look at the original differential equation, let me erase some of the writing, the annotations I made. That a little bigger. If you look at the original differential equation, you're going to notice something interesting. It was a fraction to begin with, and there was no x, but even if we're looking for the domain, we got to be careful because any x that produces a y that is 0 would cause this to be undefined. So basically, although y is not the domain, we cannot pick any x's that cause y to be 0. So it looks like our answer should just be the cube root of x, but what happens when x is 0? When x is 0, we get the cube root of 0, which is 0. And if y is 0, the original differential equation would be a problem, it'd be undefined. Your domain cannot make your original nor your differential equation undefined. It should work for both of them. So while x didn't show up and show us a problem, we know x cannot be 0 because it would cause y to be 0. So that means that although there's not a discontinuity, the derivative is undefined at x equals 0, so we can't have it. And I like to put a dotted line. Although it's not a discontinuity, it just reminds me that that's kind of my stopping point for my domain. So I need to pick the right side or I need to pick the left side. Well, the initial condition was 1, 1, so of course I'm going to pick the right side. And so that means like I want these numbers. So our answer, y equals the cube root of x, and it's important to state the domain in this one because there is no issues with it. If you look at it, there's no issues in the domain, but we got to restrict that domain so that our y is never 0. And we're going to pick 0, infinity. So here's an example where the domain gets a little funky. And these differential equations, I mean, there's a lot of them, and you'll dig deeper later on in Calc 2. I mean, there's a whole class called differential equations. But we're just kind of skimming the surface, and I wanted to show you a little bit different domain situation. So hope that makes sense and hope you're doing well.